Hello, everyone. Thanks for joining us for our next live session. I'll be your producer for our session, but before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer. Our session is being recorded. It will be available to view on demand right here on the Microsoft Reactor channel. With that, I'll turn it over to our speaker for today. Thanks for joining us.
Awesome. Thank you for the introduction, and hey to everyone. Hi, wherever you are around the world today, morning, afternoon, or evening. So my name is Graeme Foster, and I work as a Senior AI App Solution Engineer for Microsoft, and I'm based out of Australia. And we've got a really exciting AI Genius session for you today. It actually touches on some of my favorite technologies, and there's going to be some live demos and some code, and who knows if the demo gods hold up for me today. Hopefully it all goes well, but we'll see how we go. But what we're going to be doing today is we're going to have a look at how we can use Azure Functions and tools like Cosmos Database to build intelligent agents. And we're going to have a look at how we can then go a little bit further and use Azure Functions and the durable functions extensions to enable some multi-agent orchestrations. So a bunch of different technologies. We're going to touch on a lot of different concepts that I think anyone building AI agents is going to come across today. So I've got my colleague, Vanessa, who's going to be moderating the chat on YouTube. So any questions that pop up, put them in there. And if we get time at the end as well, I'll have a look through that chat and we'll try and get through as many questions as we can. So I hope you enjoy the session and let's get cracking. So I want to start off by talking about some of the different services and technologies that we're going to use today. And I think the first one that we have to look at is, I talked about running agents in Azure Functions and specifically using durable functions to do that. And you might rightly say, well, why would we do that? We know there's a bunch of really, really good platforms out there for building, hosting, monitoring, running your agents on. So let's just touch on this for a few minutes, because I think I really want to set the kind of scene on why we're using durable functions today. And I've got a nice spectrum here. So as you can see on this chart, I'm starting from a full SaaS solution on the right-hand side, like Copilot Studio. And Copilot Studio is a great place to build your agents, especially if you're maybe an end business user, or you're building agents that really want to touch the M365 universe, so integrate with SharePoint, integrate with Outlook, all of those end user business tools. It gives you a great platform, a really nice low-code experience. Could be a great way to build and host your agents. So perfectly good place to build and run agents. When we start stepping down into maybe platforms where we have a bit more customization and a bit more control, maybe there's less low code going on. In the Azure stack, we hit Foundry. So if you've looked at Microsoft Foundry, you'll have seen that we also have support for building, hosting, and running agents on Foundry. Again, it's an awesome platform. It's got some really cool integrations, and it's got some brilliant features around governance and observability, and wraps really nicely into your existing CI/CD pipelines. And we now also support bringing container-based agents. So you can pick your favorite agent framework like LangGraph or Microsoft Agent Framework, package it up into a container, and throw it to Foundry that will run and host that agent for you. Now, again, it's a great service to run your agents on. Really good if you're building greenfields or you're trying to build an agent that's got lots of reach. So maybe there are lots of other consumers that will want to access that agent. But what about if you have an existing application and maybe you just want to throw a simple agent experience inside that. So maybe you're already hosted on a platform like Azure Functions or Azure Container Apps. So that's really the kind of use cases that we'll be looking at today, is where we're already in a platform as a service. We don't want to onboard a new service to run and host our agents. So we're going to take a look at the durable extensions. Anyone that's worked with Azure Functions in the last few years may have come across durable functions. It's actually one of my favorite parts of that platform. Durable functions have been around for a while. And what they gave us the ability to do was to take maybe a long-running process. So this could be something that runs in, could be very, very quick. It could be a second, but it could be a process that takes hours, days, maybe even months, where what we want to do is model a workflow. So maybe we've got a process where we call this, then we wait for a response, then we wait for a user to interact, then we go and call something else. And then maybe we wait for a day or two for a user to respond or for another response to come back. So a kind of nice orchestrated workflow. But what we don't want to do is leave that process running for the entire amount of time. We want to free up compute. We want to make it scalable. We want it to be resilient. We want it to survive server crashes. Lots of these kind of really important things when we're building APIs. So durable functions gave us a way to do that in a pro code approach. Now, that idea of something that's long running and calls out to different services or tools, waits for interactions from other components, maybe end users or other services, that starts to sound quite a lot like an agent when you think about it, in that we're trying to model some long running process that involves generative AI and calling other tools and could run for seconds or minutes or hours or days. So what the Durable Functions team have actually released is a set of extensions for the Microsoft Agent Framework that allow us to model agents using the Durable Functions runtime components. So we're going to have a look at that today. The other thing we'll be looking at is Durable Functions themselves. The way they work, they need to store their state somewhere inside a storage engine. Now that storage engine is quite pluggable. And we're going to have a look at using a storage engine called the Durable Task Scheduler. Now, this is a really neat service because what it does is it allows us to decouple durable functions from our from Azure Functions. So that decoupling means that we can take durable functions and we can run them on different platforms like Azure Container Apps. So we're essentially going to build an agent that is very flexible, is using durable functions for its backing storage, but can run on different platforms. The other great thing about durable functions and durable agents is that they have a great debuggability. So we can run a first-rate local dev loop. You can actually build these things without a connection to the cloud. So I had a spike up a few days ago where I was using Ollama locally to run a local LLM model. I was using durable agents and running them entirely local. And the entire process I could run on a plane without an internet connection. So again, it's a really nice platform for hosting agents. And it's great if you have a brownfield environment where you just want to add an agent into it and don't want to onboard new services. So that's what we'll be looking at today. We're also going to touch on Model Context Protocol. So this has been around for a while now. Essentially, it gives us a way to build an interaction into an external component, maybe an API or a tool, once and once only, and then have that able to be consumed by lots of different AI agent frameworks or applications. So that could be Claude Desktop, it could be VS Code, it could be your own agent. Now, before Model Context Protocol, we had to build that integration for every different framework or application we wanted to expose the tool to. So MCP came along and it gave us this open protocol, meaning we could build the MCP server once, and we could have it consumed by lots and lots of different clients or hosts. So again, a real economy of scale when it came to building agents that needed to integrate with the outside world. So we're going to have a look at how we can leverage Azure Functions to easily build and run MCP servers that can then be used by our AI agents. We're going to have a look at vector indexes. So the agents that we build today are going to have to store and retrieve unstructured data. Now, the way we do this in AI agents is we often fall to what we call vector indexes. When we're dealing with AI, let's say we want to find some unstructured data. Vectors give us a really, really cool way that we can take a piece of text, a piece of context, and we can turn it into a vector, literally a list of floating point numbers, where that vector kind of embeds the semantics, the meaning, the essence of that content. It's kind of like profound when you put it like that, but it's got this really beautiful property, which is that we're essentially taking text and we're taking the language part out of the way we store it. And instead, we're storing the kind of meaning and semantics of the text. Why this is really good when we're building AI agents is that, let's say we create vectors representing a lot of different content. This could be thousands, millions of documents. And we store these vectors in what we call a vector index. Vectors are beautiful because there's a very simple mathematical way and a very efficient mathematical way to find the vectors that are most similar to a query vector. So the approach basically is that we have all these vectors that are pre-calculated and pre-stored, and then somebody comes along and maybe they input a query saying, I want to find all code snippets related to class XYZ. What we can do is we can use our LLM to create an embedding of that query. So that turns the query into the same floating point number array, and then we can throw that at a vector database and say, hey, you've got millions of vectors stored. Give me the closest vectors that match what the user is asking for. We sometimes call it a similarity search because we're finding similar items, but we're using the vectors which are really capturing semantics and meaning of the text rather than the actual text itself. Interestingly, we can also embed other things, not just text, but we can embed images, graphs, and other types of data. So again, a really powerful concept. And if you're building AI agents, you're going to come across vector indexes a lot. One thing I should have said on that as well is we're going to use Cosmos database as support for vector indexes. Lots of different tools out there support vector indexes. Today, we'll be looking at Cosmos database. Again, if you're building or you've got a brownfields application, you've probably already got a database in there storing your application's data. So using the vector index support in that native database, this gives you a really nice, easy way to build your agent without having to bring in new services. So this is the last slide until the end, just to give you a summary of the application that we're going to be looking at today. It's a little application called Snippy. The link to the repository should have been shared in the YouTube chat. So you're very welcome to clone the repo and play along today if you want to. And the different components we've just looked at are going to come together to create an application that is going to expose a few MCP servers. So this is going to allow our AI agents, whether that's VS Code or the MCP inspector or Claude Desktop, to access those tools directly from their surface. And we're also going to create a couple of multi-agent orchestrations using those durable agents that can then use the information that our MCP tools stored in the Cosmos database to build some comprehensive documentation based off some code snippets that we capture in our VS Code session. So we're going to bring all these things together and we're going to have a look at the code and walk through the way that we can structure, build, monitor, and deploy an application like this. So with that, I'm going to drop out of PowerPoint and we're going to go into VS Code. So just for those people that are interested, here's the link at the top here to the GitHub repository. And the second tab along here has got a link to the actual lab that we're going to be walking through today, step by step. So feel free to play along and let's get into VS Code. Okay, so if you've cloned the repository, the first thing I want to bring your attention to, it's not specifically anything to do with agents, but there's a little file in here which is called azure.yaml. So this is a really nice little file that can help us to deploy infrastructure and applications to Azure environments. If you're familiar with Azure, you might have come across a infrastructure language before, which is called Bicep. You may have used Terraform as well. So these are languages that allow us to create infrastructure inside a cloud platform. Now, that's only one part of building and deploying an application into a cloud environment, because we also have to get the actual application code up there as well. So what this azure.yaml file is going to do, it's going to let us use a CLI tool called AZD, which stands for Azure Developer, and AZD will also deploy the application code for us as well as the infrastructure code. So we can bring the application together, and in one very simple command, like you can literally download this repo and go into your terminal and just type AZD up, and that will provision everything for you. Now, we're not actually going to do that today. We're going to walk through it in a little bit more details. But what I did do a few days ago was I actually ran another command, which was called AZD provision. You can see that one here. And AZD provision will go off and deploy the infrastructure into Azure. So I've just wanted to get that set up, and then we'll walk through the actual application code deployment later. So there's a few steps in the repository for working through this. There's a few little bits of information you need to enter, but this is going to take a few minutes if you do deploy it. It's going to go and deploy an Azure Function app, some storage, a Cosmos database. It's going to deploy Azure OpenAI as well. We're going to set up a GPT-4o mini and an embedding free small model. And then it will create a Microsoft Foundry project, App Insights, the kind of usual things that we need to run APIs and applications. And it will also provision the durable task scheduler, which we'll use for running our durable agents later. So if you've run this, it'll take a few minutes to do. That's okay. What we're going to do in the meantime is we're going to start to have a look at some of the code that we'll be bringing together to build and host our MCP servers and tools. So we'll have a look at how Azure Functions makes it really easy for us to expose MCP tools, and how Azure Functions lets us build durable agents. So what we're going to do is, if you are following along, let's go into a file called function_app.py. So I'm on a Mac here, and I've just used the Apple P command to bring up this little search bar, can make it easy to get around VS Code. So we'll drop into the function_app.py file here, and I want you to go to about line 65 in here. So we'll start at looking at how we expose MCP servers and tools inside of Azure Functions. So you'll see there's this little Python class here called tool property list. Now, if you think about an MCP server is like a gateway to a bunch of MCP tools. So the tools are actually the things that will integrate with downstream APIs. And in order for an LLM to decide it needs to call an MCP tool, it needs to know about some information about that MCP tool, what it does, what properties it has to pass to the MCP tool. So we're using this tool property list to basically set up 3 properties in this case for one of our MCP tools, which is called the save snippet tool. This is the one where we'll be able to select a piece of code inside VS Code and then ask our agent to save that snippet so we can use it later. So this tool property list has got 3 properties. And when we define these, there's a few little bits of information we need to give them. The first is a snippet name. So in this case, my MCP tool expects every snippet that gets saved to have a name associated with it. Now you see a little bit of metadata. This is a string, pretty straightforward. But the important one is here. You can see this actually moves along quite a lot. There's this little slider bar. It's a unique name or identifier for the code snippet. Provide this if you have a specific name for the snippet being saved, essential for identifying the snippet later. It's quite a lot of text, but it's actually super important that we are very descriptive when we build our MCP tools. You see, at the end of the day, what's going on is we're just telling an LLM, hey, there's some things that you could possibly do. Here are some external tools that you could use if you think they are useful to help drive the user towards what they're trying to do. The way the LLM knows to choose that tool is all on the metadata that we provide it. So when you're building MCP tools, these descriptions are super important. Be quite verbose on them. So the LLM really can see and understand when to invoke that tool. My little save snippets has got two other properties. We've got a project ID, so I want the users to be able to organize snippets by project if they want. In this case, it's an identifier for the project, but we're going to tell the LLM, like, it doesn't matter if they don't pass it in, just set it to default project. That's fine. And the other thing we have is the actual snippet itself. So this is the code that we're going to go and store inside the Cosmos database so we can retrieve it later. So what we're now going to do is we're going to go and have a look inside the Python code that actually defines the MCP tool itself. So these are just the properties we want to pass into it. You'll see there's a few other sets of properties as well if you look through the code here. But go to about line 174 inside this file. And this is where the Azure Functions extensions really start to come into play. If you want to build an MCP server, there's a little bit of work. There's a few things you have to do normally, right? Let's say you're building an MCP server, running it on a standard Python web server or VM. You'll need to get an MCP SDK, and then you'll have to work out which hosting, whether you want to use, I'm not sure what Python web servers are actually. If you're in a node world, whether it's going to be Express or some other web server, a lot of plumbing that you have to put in there. We're using Azure Functions, and we're bringing in some Azure Functions extensions that allow us to just delegate all of that hard work to the Azure Functions runtime. So in this case, you can see that I'm going to annotate a method, and I'm going to say, look, this is an MCP tool trigger. So Azure Functions will now do all the hard work of creating the endpoints, wiring up the JSON RPC protocol that MCP uses, so that I can just very easily trigger my MCP tool, and I don't have to write much code to make all of that plumbing happen. It's just all in this one little annotation. So if we have a look through this, there's a few bits of information that are pretty important. So we've talked about the annotation itself. You can see here, there's an argument name, which is context. So those properties that we just saw in that other little Python piece of code, what we're saying here is that we want those properties to get passed in to this method. You'll see when I highlight context, the MCP save snippet also highlights context. So that's just a little bit of wiring in Azure Functions. It means that it's going to pass the JSON object in containing those MCP properties that the LLM decided to invoke the tool with into this method. We've got a tool name. An MCP server can host multiple tools. So we just identify each tool by a name, pretty straightforward. And then we have the description. So just like the properties, important to make this pretty verbose so that the LLM really understands whether it's worthwhile calling this tool based off the current state of the conversation. So you'll see, again, this is one of the longest lines in this code base. It just keeps going on and on and on. So we're very descriptive about it. And then we have this final property down here, which is called tool properties. So here we're just referencing that little Python tool property list we saw a minute ago, and we're turning it into JSON. So that's how all we have to do actually to create an MCP tool and server inside Azure Functions. So just with this, we now have got a tool that can be invoked by an LLM using the MCP protocol. So that's pretty cool. So there's another really cool input here as well on the Azure Functions that I want to call out. So we talked earlier about vector indexes and what a vector actually represents. So how do we turn content into a vector? Now, again, like, you could write code to do this. You could open your, let's say you're using Azure OpenAI. You could use the Azure OpenAI SDK. You could create a client. You could then call the embeddings model with the content. And it's all pretty straightforward, but it's just code that you have to write. So one of the Azure Functions extensions we can use is another annotations, which is called the embeddings input. So what this is going to do is it's going to allow us to identify some data being passed to the Azure function via MCP. And we can almost kind of sit in the middle and say, okay, let's actually go to an OpenAI model and create the embeddings for this content without the user having to do anything inside their function code. And when we've got those embeddings, you can see here arg name is embeddings. We're just going to pass those in to the actual method parameter list itself. So again, I don't have to write any code to do that whatsoever. I just use Azure Functions, which will do all the hard work, all the plumbing for me. I give it the argument name. I tell it exactly what I want it to embed. So in my case, we're going to go to the arguments and find the snippet property. If you were to go back to the tool property list, you will see there was a property called snippet. We're going to pass some raw text into the embeddings, and then we'll just specify which embeddings model we want to use. Now, in my case, we've employed a text embeddings 3 model, so that's the representation that we will get back. So again, this is all built into Azure Functions, which just makes it super easy to actually go and integrate with this. And then from inside the tool itself, what you can see is that we can go and find the actual MCP properties that were passed into my MCP tool. And we can just load some JSON in basically to the context and then go and get those arguments. And then from this JSON object, we can go and get the exact properties the LLM decided to call us with. And similarly with the vector embeddings, if we scroll down a little bit more, you'll see my embeddings just come in as the exact output that came from Azure OpenAI. So it's kind of unfiltered really by Azure Functions. It just passed straight into me. I load that into a vector array, and then I can go and index into that and go and find from response data embedding. So if you've ever used Azure OpenAI or OpenAI, you'll probably recognize this little structure as what responses look like when you make an embeddings call to Azure OpenAI. But again, the really cool thing is we didn't have to write really any code to make that happen. We just annotated our method inside the Python code, and everything happened for us and was plumbed in by the runtime. Okay, so that's the MCP servers, the MCP tools, and how we deal with getting some embeddings input into our MCP tools. There's a few other MCP tools defined in this class as well, but they all follow a fairly similar pattern. So what we're going to do now is we're going to go to another file. So I'm going to Apple P, or it's Control P if you're on Windows. And we're going to go to a class which is called durableagents.py. So this is basically a class that holds all of the definitions for our agents that we want to orchestrate using the Durable Agents extension. So what I want you to do, if you're playing along, is let's go to about line 135, and we'll start from the beginnings of how we set up agents. So we're using Microsoft Agent Framework inside this class because it's got really nice integrations into the Durable Agents extensions. It's pretty cool. It's a very pluggable framework. So what I mean by that is line 135, you can see that we're using Azure OpenAI here. You can happily use, let's say, Ollama. I think we just announced support for Claude today. That might have been for a different framework, but you can pick pretty much most inference models, and there will be a plugin for the Microsoft Agent Framework to enable you to inference within your agents using that LLM type. So in my case, it's Azure OpenAI. We got a few little bits of information in here. So to create a connection to AI, we're going to use this class called the Azure OpenAI Chat Client. So I guess the only really important thing to call out here is that there's a couple of different ways we can authenticate against Azure OpenAI. We always need an endpoint and we always need a model name. They're just kind of like non-negotiable. But we can choose to use an API key, or if we want to, and I would recommend you do this because this is the most secure way to actually access a service like Azure OpenAI, we can use Azure's RBAC, role-based access control mechanisms to access that. And that's exactly what we're doing in the second approach here. We're using this Python class called the default Azure credential. This is really cool. If you've ever used default Azure credential before, it's kind of like a set of stepping stones for how can I try and get a credential to speak to a service in Azure. So this same class, if you're running inside Azure and you have access to a Azure managed identity, whether that's a system identity or a user identity, it will work that out and get a credential that way. If you're running in Kubernetes, it will have a look for a workload credential, which is a way that we can integrate Azure identities into Kubernetes. But importantly for me here, if I'm running locally, then this will start to look at things like the Azure CLI. And if the Azure CLI tool is signed into Azure, then it can get a credential from there as well. So really just wanted to point out, like, we're going to use the Azure OpenAI chat client to for the LLM for our agents, but there's different ways we can authenticate about that. So let's move to line 155 here. And let's have a look for how we actually create an agent using Microsoft Agent Framework. And it's pretty straightforward. So I've got my first agent here, which is called the Deep Wiki agent. So this is an agent that is going to help me generate some fairly comprehensive wiki-like documentation, given a set of stored code snippets that the user stored using the MCP server. And you can see, like, a simple agent really doesn't need much configuration at all. I'm using this chat agent class that comes from the Microsoft Agent Framework. We're going to tell it, this is your chat client. So in my case, that is the Azure OpenAI chat client up here. So the agent knows where its inferencing model is. We're going to give it a name as well. And then the next two things are the most important parts to an agent. Agents, if you want a simple definition, think of it as like tool calling in a loop to try and help a user achieve a goal. So that's like an ongoing conversation where the agent is given a task. It's told what it is there to do to help the people that are using it or the other agents that are using it. And then it iterates on that. And as part of trying to achieve that goal, it will use tools as it sees fit to help it get there. Really important, the first thing is the system prompt. So I'm going to go into this actually. I'm going to hit Command and then I can click to go into my system prompt. These are the instructions for my agent. They're quite long, quite verbose, and we don't need to go into them in too much details. But you'll see we talk a lot about vector search. The thing with our Deep Wiki agent is our Deep Wiki agent will need to go and find code snippets. How's it going to do that? It's going to use a tool. So if we go back to about line 155, I think is where we were, you can see that when I declare my agent, I can give it access to tools. Now, in my case, I'm just going to give it access to a very simple function, actually. A lot of people think that when we talk about tools, we always mean MCP. But if you go back before MCP, we had tool calling inside large language models. It was often a local function that we would invoke. And that's all we're going to do here. I'm going to present a tool to my agent, and it is a local Python function. So when the agent decides it needs to call it, all that will happen is the Microsoft Agent Framework will invoke this function for me. And you can see that on this tool itself, it takes in about 3 parameters. So we've got the query, we've got, which is what the agent thinks it needs to search for. So if I say I want you to create some wiki about the architecture of my application, it might pass in a query such as like architecture code snippets or find me architecture documentation. The other thing we pass in is we've got this K property. When you're dealing with vectors, you'll often see the letter K quite a lot. In our case here, it's literally the number of documents that we want to return. So how many snippets do we want to get back in? We're going to default it to 30. But if you said to the agent extensively search the documentation, it might decide to pass in a number much higher than that. If you say to it, hey, there's only going to be a handful of documents, it might choose to pass in a smaller number than that. And then the project ID. So again, if you remember the MCP tool, we could organize our snippets by project. The default in this case is going to be to search all projects, which is where the asterisk comes in. So we'll just take a quick look inside this tool. Performs vector similarity search on code snippets. So there's a couple of things going on here. The first is that we are actually going to use Azure OpenAI directly to create embeddings. So we're not using the annotation on the function for this particular example. We're going to go and get a token that we can pass to cognitive services, and then we're going to use the Azure OpenAI to go and create embeddings based off whatever the agent thought it needed to search on. When we get our embeddings back, we're going to call Cosmos database. So we have this little function here, which is Cosmos ops.query similar snippets. Now, internally, let's have a look on the documentation here. We can see that what this is going to do under the hood is it's going to issue a SQL statement to Cosmos. And this is just select top number of rows that the agent, there's the K again, and we want to get back, importantly, the code. And we're going to use this Cosmos database function, which is called vector distance. So this is really the guts of the query here. The vector distance function will look at all of the code snippet embeddings that are stored, and it will calculate how similar they are to the vector that the agent wanted us to search over. And then we're going to order by the vector distance and return those results back to the agents once we've got them. So that's kind of what's going on when we declare those agents. So let me go back to this file again. And again, you'll see inside this particular class, there's a few other agents that are created as well. But very, very similar approach, just a different name, different instructions in this case. So how do we actually run and host these agents? So let's go to about line 217 inside this file. So what we're going to do is we're going to use another extension class from Azure Functions. And in this case, we're going to launch what's called an agent function app. So this is, I think if you go into it, this is actually literally an extension of the Azure Function app class. But in this particular overload of it, we can pass in a bunch of agents. And what will happen here is that Azure Functions is going to create some endpoints so that we can call those agents from an external client if we want to. And it will also set up a health check as well, which can be quite useful. Now, we talked earlier about durable agents. Again, if you think about an agent can be long running and it can have a long running conversation with an end user. So we need somewhere to store that conversation. Now, if you built an agent a few years ago, you might have to have stored that in your own database, maybe in SQL, maybe in Cosmos. If you're using something like Copilot Studio or Microsoft Foundry, then they will take care of storing that conversation for you. What the durable agents do under the scenes is they use the inbuilt storage facilities of durable functions to store the conversations for you. So again, that's another reason why these durable agents are actually really cool. We don't need to worry about setting up databases to store the conversations. It just all happens for us, which is pretty neat. So when we set this up, we're going to get a bunch of endpoints that are generated for us, and we're going to get this conversation storage for free, which is great. Okay, so that's how we run and host the agents. Now, we talked about multi-agent orchestration. So I'm going to drop down to line 251 inside the code. So this is where we start to get a little bit deeper into the world of durable functions. If you remember from earlier, I tried to explain a durable function as a way to model a long-running workflow such that we don't have that workflow consuming CPU cycles and sat in a waiting state for all of the time. Instead, the way these things work is that we break the workflow into two types of components. The first component is the orchestration. So the orchestration is really the pathway through the workflow. And then the second type of component are what we call activities. And the activities are the things that actually do things. So that might be a call to an agent that needs to go off and interact with an external system. Might be a call to an API. And what durable functions does, which is really cool, is it separates the two of those things. So the orchestration only runs when it needs to. And when it needs to call off to an activity, the orchestration literally unloads from memory. And then the activity gets scheduled. And it might not even run on the same VM under the hood. It might just run somewhere else. So it gives us this way that we can really scale out these orchestrations, or these agents in our case, so that we can host loads and loads of them and not really worry too much about consuming too many resources on a single VM. So it's a really nice scaling pattern. The way we signal to Azure Functions that we are using one of these durable orchestrations is we use this little annotation here called the orchestration trigger. So in our case, this will kick off the workflow. And then it's pretty straightforward. So this is kind of like, I think the most important things to show here. Let's go for a bit of code in a bit more detail. If you go to line 284 on here, what we can see is that we make a call to get agent. So this is literally going to give us our instance of this agent. So when I say our instance, what I mean is that when we make the call to get agent, we're passing in this property called context. Context is specific to an individual run of the workflow, meaning I'm going to get an agent that is just for my run of this workflow. Okay, so we're not sharing state between multiple runs and things like that. So once we've got hold of the agent, what we can then do is we can call this run method on the agent. So all this is going to do is it's going to schedule the agent to run. The important thing is that there's this yield statement here. So when we execute this under the HUD, and this is a little bit weird to get your head around the first time, this agent does not run straight away. Instead, what happens is the durable functions environment kind of says, okay, I need to run this agent. So I'm going to make a mark inside my own state storage to say, let's get this particular run happening. The yield statement just means that the method will literally yield. So that's how we unload the method from the process. Then in the background, durable functions is going to spot that there is a request to run this agent, and it will pick it up and it will go and schedule it on a machine somewhere. When the agent has run, it's going to give back its response, whatever that might be. And then in that case, the response gets stored in the same durable function state storage. At a different point in time, the orchestration is going to wake up. It's going to go, okay, this is cool. There is a response from an activity that I kicked off. So the orchestration will start at the top and it will run all the way through and it will get back to line 287. It will call deepwiki.run again. But the difference this time is that has already ran and it already gave a response. So instead of the method stopping like it did the first time around, the response is loaded up into the initial wiki and the method continues. And then repeat the reprocess. So what we're doing here is we're literally sequencing two agents so that they run one after the other. We're going to run deepwiki first to get the initial wiki. And then we're going to run it again. We're going to ask it to enhance the documentation with more code examples and best practices. Gives us back the refined wiki. Then what we'll do when this one's finished is we'll go and get the code style agent, and we're going to then run that. And then we'll do a little bit of work to kind of bring out the results from all of those three agents together. So it's a very structured workflow, is this, right? This is not like multi-agent orchestration where we don't know in which order agents are going to speak to each other. It's actually quite different. This is very much like this agent will run. We're going to wait for it. Well, we're going to yield our process and it will come back with a response at some point in the future. Then the next agent will run. Same thing. Then the next agent will run, and then we'll bring it all together. So think of it of a way to like model a process as opposed to a more kind of organic multi-agent orchestration. So it's a super simple programming model. And the beautiful thing about this, as I mentioned earlier, is you can actually run this locally. So as we'll see in a minute, there are emulators we can use to try all of this out without deploying anything into the cloud, which is, I think, really, really exciting. Okay, so the last thing, actually, I think we already had a look at this one. So I was going to show you the vector search tool, but I think I got ahead of myself because it's quite an exciting session, is this one. So this is just a tool that was used by the agent, which went off to query Cosmos database to bring back the similar vectors. Okay, great. So that's the main bits of the code that I wanted to show you. So what we're going to do now is we're going to move on to actually setting this up and running it locally. So what I'd like you to do if you're playing along is let's just open a new terminal up. And what we're going to do is start off by creating a virtual environment for this. Actually, one thing I didn't point out earlier, this sample comes with a dev container. So if you just want to pull it down locally and you don't want it to affect your existing environment, when you open it, VS Code will ask you if you want to open the project in a dev container. And if you do, it's just going to create a Docker container, and then it will literally run VS Code server inside that Docker container. And then you can basically play with the application without installing anything on your local machine. So pretty nice way to kind of experiment a little bit. But we're going to go, well, I'm in the source folder already, but if you're just in the root of the repo, then let's get into the source folder. And I want to start off, we're going to create the virtual environment using this command, uvvm.vm. So I've already created one anyway, but this is going to create a virtual environment so that when we're installing Python libraries and things like that, they're local to the code base. They're not going to be in your user-based environment where they can interact with other libraries and you can get mismatches and things like that. So you see, once you do this, you get asked to source it so that we can set up the environment properly. So that's great. I think that's slightly different on Windows. There's still an activate script in there. So let's go and install the components. So uv pip install -star requirements.txt. So there's a few packages in here. UV just makes them quite a lot quicker from what I've seen to install than pip does if you use it directly. So that's pretty cool. Now, when we run this locally, we're not going to run everything locally in this demo. We're still going to access the LLM in Azure, and we're going to access the Cosmos database in Azure. So we need to set up our local environment variables so that our Azure functions know where those things are. So when we looked at the azure.yaml file earlier, I'll just go and pull that back up. What you may have seen if you were looking in here is that there were some hooks in here. So we had a pre-provision and a post-provision hook. The post-provision hook basically runs a file that will interrogate the environment that's just been deployed, and it will help us set up our local .settings.json file. So if you were to open this file up, what you should see is that there are a bunch of settings in here that point to the infrastructure that has just been deployed into Azure. So in my case, and in your case too, you'll see that the durable task scheduler we talked about earlier, we're going to use a local emulator for that. So we'll look at that in a minute. But for Cosmos and Azure OpenAI, we're pointing up into the cloud for running this locally. So once you get those set up, and you can regenerate them if they're not there, that's all pretty cool. There's instructions in the documentation on that one. We're going to start Docker Compose. So why are we using Docker Compose? Well, we need a few emulators to run this application. We need to get some storage because Azure Functions under the HUD require a storage account. So for that, we're going to use a Docker container called Azurite, which is an Azure storage emulator. So that's in the Docker Compose file. And then we're going to need access to an emulator for the durable task scheduler. So again, there's a really nice emulator for this, which is the DTS emulator. So we're going to pull that down as well. So this is going to give us all the kind of infrastructure and plumbing we need to run our Azure functions and our durable agents locally, which is pretty neat. Now, for what it's worth, there is also a Cosmos database emulator that you can pull down, if I recall correctly. I'm fairly certain there is anyway. So that's something else you could run locally if you wanted to. And then if you want to run the whole thing locally, as I mentioned earlier, Microsoft Agent Framework does allow you to connect to Ollama models as well. So you can use an Ollama client as part of your Azure agents. But what I'm going to do is, and I think this is my Docker one, so let's just have a look which directory we're in. We're in the main one there. We're going to use Docker Compose up -d. So I've now got my storage and my durable task scheduler running, which is great. So we'll just do a PS on that. And you can see there are a bunch of ports that are exposed by these things. And we're going to have a look at the UI for durable task scheduler in a minute as well. So what we're going to do now is we're going to start up Azure Functions. So I'm going to go into another one here. And we have a CLI tool, which is called Func. I think there should be instructions on the documentation how to install this. But what we'll do is we're in the source folder, which is great. So we're going to do func start. So this is where if the demo gods are going to smile on me, things will start working. And if not, then you'll see me kind of scrambling a little bit for the next 20 minutes or so while we go through the demos. So let's see how we go here. So the function tools are starting up. I'm okay with yellow. I ran this yesterday and I got quite a lot of red back at me, but yellow is good. I'm okay with that. So if all goes well, we should get a whole bunch of Azure functions exposed to us. So let's see. This is where I need some background music from the producer to pass a little bit of time. I really hope this is going to work. It didn't take this long yesterday. Okay, here we go. Great. This looks good. So my Azure functions have started up now. You can see there's quite a few different endpoints that have actually been created for me. So some of these are related to the agents. Do you remember earlier when we created the agent, we asked to expose a HTTP endpoint for it? Well, here they are. You'll also see in here, we've got our orchestration that we looked at. So this is the multi-agent thing we'll be using. And then all of those MCP tools as well. We looked at the codes, the get snippet and the save snippet one. So these are all here as well and can be consumed by MCP. So if we want to just test these locally, what we've done as part of this sample is we've actually exposed some HTTP endpoints. And there's a lovely little file in here, which is called test.http. So again, Apple P it, it'll just come up test.http. And this basically has got a bunch of little tests that we can use for running locally. So you can see local endpoint 7071, and then we can have a go. We can try and create a code snippet. So we can just hit send request and we can see what happens on this. So I've pressed that little send request button there. And hopefully, because I did have some issues with my Cosmos database disabling public access earlier. Okay, this is great. So we can see that my function basically has come back with a 200 OK. And what we've done is we've gone and created a snippet called test snippet. I gave a project ID as well. That was the code that we wanted to save as a snippet. And you can see, pretty cool, there's the embedding. So that's that annotation we looked at earlier kicking in, calling the Azure OpenAI model, using that annotation to go and create embeddings. So that's all pretty cool. What we'll do is we'll try and retrieve that snippet. So I'm going to grab the test snippet name there. And I think there is another one in here, which is the get. So here you go. We're going to call it get request to API snippets test snippet. And if all goes well, and I think it just did, yeah. So there we go. So we've got back the test snippet, and there's the code. It was a code snippet, and there's the embedding again inside it. So this is really cool. In the interest of time, I won't go through more of these, but we do have HTTP endpoints that you can use to test pretty much all the functionality that we've looked at so far. Okay, so let's move on to MCP tools. So we know that our Azure functions are exposing MCP tools. How can we use these? So if you look inside the code, you'll see there's a folder called .vs code. And this is actually really cool. This allows us to kind of create contextualized VS Code setups for our projects. So in this case, we've got this little file called mcp.json. And let's close some of these down. mcp.json lets me do is specify some MCP servers that I think are going to be useful for this particular repository. Now you'll see down here, I've got two servers that have been set up. I've got local Snippy and I've got remote Snippy. So we won't worry about remote Snippy so far, but my local Snippy is a HTTP MCP server, and here's where it's pointing to. So I'm going to click start on this. And if all goes well, then we can see that this is running, and we can see that it's discovered 5 tools, which is exactly what we expect. If you see in VS Code, if you've got the GitHub Copilot screen open up, there's this little configure tools button down here. So we can select that. And then what we can do is find our local Snippy tool. And we can see the tools. These are exactly the same tools that we defined inside the Python code. And they're all here. And I've just enabled them so that I can use them as part of my GitHub Copilot chat, which is pretty cool. If you're really into kind of like debug logs and things like that, then what we can do is we can use another command, which is Apple Shift P, which allows us to push some commands into VS Code. and we can say, in our case, MCP list servers. We can go and select our local Snippy, which is running, and then we can say show output for that. And in the log file, you can see all the interactions going on to your MCP server. So it can be really useful for debugging it. Okay, so let's use it. So we're going to go into GitHub Copilot, and down here, what we're going to do is let's go and find a source file with something interesting inside it. So I'm going to go and find and highlight 3 lines of code in my durable agents file. You can see they're selected here. And I'm going to say hashtag local Snippy. So hashtag just gives us an easy way of specifying or telling Copilot, hey, I really want to use this for this particular interaction. GitHub Copilot would probably work it out without the hashtag, but this just kind of helps it a little bit to be guided. So local Snippy, please save this code snippet in project Graeme test as durable agent. So we'll hit enter on that. And if all goes well, we're going to see a few things happen. So the first thing, okay, we can see that Copilot has come to me and it said, hey, I want to run this MCP server. Is that okay? So right now, I haven't given it permission to run this without asking me. Always think about that when you're using MCP servers. There are quite a lot of exploits out there. So you really want to trust the MCP servers that you're invoking. In my case, it's all good. Let's call save snippet on that. And we can see we've got a little tick, which is brilliant. And if all goes well, there we go. We've saved the snippet store, name durable agent project Graeme test. So that's really awesome. So let's just prove that that actually saved. We'll just go to hashtag local Snippy. Please retrieve the snippet Graeme test from the project durable agent. And again, if all goes well, actually what I should do as well is go to the Azure Functions output. So I'm going to pull back up my terminals inside VS Code, and we should see a whole bunch of log files going through here as well. So we can see there's database interactions going on. We've got upserts into Cosmos database. We've got functions being executed, et cetera, et cetera. So, and there we go. So, oh, it's actually saved more than I expected it to for some reason. That's quite interesting. Here's the snippet from Project Graeme test. Okay, well, that's something I'll have to look in later. Demo gods never go to plan, and you can see in this scenario that it hasn't quite worked. But let's not worry about that too much. We're going to move along anyway and move along to the multi-agent orchestration. So the last thing I want to do is I'm going to go into Copilot. I'm going to say local snippet. Please generate comprehensive documentation about my saved snippets in the, I think it was called test project, wasn't it? If I recall correctly, durable agent project. So a bunch of things are going to go on here. Now, this is going to be quite interesting. And once I've done this, I'm going to show you some, in fact, let's do that now. I'm going to open up a browser. And I'm going to go to, let me pull one up here. Give me a second. I'm going to open localhost 8082. So when I started my durable functions emulator, durable task scheduler emulator, one of the things that it did was it opened up a dashboard on localhost 8082. So this is where I can go and see all the orchestrations that are running, that have run, that have failed, and get a really good visibility into what's going on. So I'm going to basically use this multi-agent orchestration. For what it's worth, here we're actually exposing the multi-agent orchestration as an MCP tool, right? So maybe not quite what you'd expect, but in my case, I don't need to have an ongoing conversation with this agent. It's just a one-stop call for me. So it kind of works to expose it as an MCP tool. If you're getting into exposing multi-agent orchestrations for your organization, you might want to think about things like agent-to-agent protocol or other ways that you can make that agent consumable. There's nothing wrong with exposing a multi-agent or an agent using an MCP tool, but it's just maybe it kind of limits the ways that you can use that agent. Works really well for me though. I'm going to click allow on this. And what we should start to see behind the scenes, I saw some red text there, so I'm hoping this is going to work, is we're going to go and generate the comprehensive documentation. Now, what I'm going to do is flick back to that browser that I had open. And I'm hoping, here you go. So you can see there's a documentation orchestration that started off inside my emulator. I'm going to go into that. And what we can see is, let's see if we can expand that. My orchestration started off, and then it went and it ran the DeepWiki agent, and then it ran the DeepWiki agent again, just as we saw when we were stepping through the orchestration. And then it went and ran the code style agent. So this is really cool, right? We can see the interactions, we can see what properties were passed in to these different agents to kick them off. We can see the responses that they came back with as well. We can see there's an error inside there, failed to complete the prompt 400. Again, I'm not going to worry about that too much because otherwise we might not finish the demonstrations today. But hopefully this kind of gives you a very brief insight into how much debugging in kind of observability we can get into durable functions. I talked earlier about how my multi-agent orchestration would run one agent after the other. You can see on the waterfall chart here, like the orchestration lasted for this whole blue bar of time. The first agent ran here, and then the second agent ran straight after that one finished, and then the third agent ran after that one finished as well. So, you know, we can, again, see that they were sequenced properly. Oh yeah, definitely there's a problem down here with my Azure OpenAI chat client. So again, I'm not going to worry too much about that one right now. But what should have happened is that our agent ran and it should generate comprehensive documentation for me. What should have happened is that a markdown file should get generated, but it hasn't. And hopefully we can run the Azure version of the agent in a minute and have a look at the markdown that gets generated. So this is the local debug loop. Some issue, let's see if we can work out exactly what it was actually. Service compelled to complete the prompt. Yeah, I'm not sure. It's possibly an authentication issue. Maybe my Azure policy has kicked in and decided that it's not my day to be running these LLM calls, which is a shame, unfortunately. Okay, so how do we deploy this thing to Azure? So we talked a lot about AZD and the Azure Developer CLI early on. Now, if you've got this installed, then once you've provisioned the infrastructure, we can use another AZD command, which is AZD deploy. When we use that, what it's going to do is it's going to look at the azure.yaml file that we had earlier, and it's going to see inside here, look, there's an API service, and it's pointing to a source folder, and it's a Python function that we want to host, right? We then have tags inside the infrastructure that allow AZD to say, here is the function app that needs to host this API. So what AZD will do is it will zip up the function app, it will deploy it into Azure and deploy it into the correct function app for us. So if you do that, that might take a few minutes. But again, I'm going to skip ahead because I've already deployed this app. And what we're going to do now is we're going to go and connect to the cloud version of this MCP endpoint. Now, if you're following the documentation, there's a couple of steps involved to actually get the credential to be able to call this MCP tool. If I open up mcp.json over here, what you'll see is that we need to pass an authorization key into the Azure function, right? This makes sense. We're not hosting it locally. This can be accessed by people out there on the internet, so we need to protect it. There's some instructions on how to get that function app key, but I've already done that and set this up. And my function app name has also been set up so that my MCP client knows how to connect to the Azure functions that are hosting these MCP servers. So what I'm going to do, I'm going to stop my local Snippy and I'm going to start the cloud Snippy instead. And we're going to go and have a look at the output. So I'm hoping that this is going to work better for us. So let's go back and issue some pretty similar prompts, but instead of addressing local Snippy, we're going to address cloud remote Snippy instead. So remote Snippy, please save this code snippet. And again, let's go back and select some code inside this app. And we'll save it in cloud test as durable agent. So hopefully this is going to work for me. I'm glad this is more about walking through the code and less about the actual code working. It's always fun when live demos fail. At least it shows it's live though, which hopefully makes it more exciting. So we'll call save snippet on the remote MCP server. Okay, we have a tick, so I'm happy about that. So all looks to have gone okay, and we have run that one correctly. So let's now prove that's worked. We'll go to our get snippet on remote Snippy. Please get the snippet cloud durable agent on the cloud test project. Okay, so hopefully my Azure OpenAI model is working better up in the cloud than it's working down here, else this is not going to work. Do you remember when I ran get snippet the first time and it didn't give me back what I expected? I got a feeling that, yeah, here we go. I wonder if this is the same problem going on here. I got a feeling this might not work when we run the actual multi-agent orchestration up in the cloud as well, but that's okay. We'll give it a go and see what happens. So what we'll do finally is that there's a little script inside the application that will give us the URL of the dashboard where we can monitor the remote orchestrations. So you'll see here, script get DTH dashboard URL. So we'll execute that. And I think I've got it captured in case this script doesn't work anyway, which is pretty good. So give that a second to come through. Okay, great. So let's go into here and we'll pull that onto this screen over here. So this, again, the emulator is really nice. Like the dashboard literally looks exactly like the dashboard that we see when we run the local emulator. This is all authorized using Entra and things like that. Actually, I'll tell you what, I'm going to use a different browser profile, one that I know can access that. So bear with me again. Let's just go and find that little snippet, copy this. Where are we? Just from here onwards. Put that in there. So this should take us into the dashboard. And here we go. So we are up now on the cloud version of the dashboard. So actually, luckily for me, if this doesn't work, there's one that I did do the other month that we can have a look at the output of that as well. But let's go for it. And we'll say remote Snippy, generate comprehensive documentation for all the stored snippets, please. I'm one of those people that always says please to my agents. I watched a talk from Scott Hanselman once, and he made this really good point, which is like the prompt in your LLM calls is all about setting the context in which the LLM is going to output the next token. So words like please, even though they might take up a bit of extra processing and things like that, maybe just set the model on the nicer side of the internet, which is kind of where I want my responses to come from. Whereas when you get a bit kind of like snarly or salty at the models in your prompts, then maybe you're kind of pushing them towards the lesser nice side of the internet. Okay, so let's go to the dashboard now. So this should be running. So what we hope to see down here is a second orchestration kicked off. So here we go. And we can see that it has completed. The question is, though, was there some kind of deeper problem with my agents that was stopping them from working? And let's have a look. Okay, now this actually looked pretty good. We can see we've got token counts coming back. So again, like really good insight, right? I can see here literally what my agents are doing, and I can see that the responses have completed successfully and things like that. So if we go back to VS Code, then I'm hoping down here, comprehensive documentation generated. I'm going to say to it, can you save the documentation in a local file, please. So let's just see, here we go. It's going to create an existing docs directory as comprehensive documentation.markdown. Okay, great. And what we can do is we can open this file up here, and we'll right click on this and say open a preview. So now we can see this is basically the output that came back from our MCP servers. We've got a project overview. It's basically gone and worked out what the project is doing. It's had a look at, you can see some of the snippets that it saved. I've saved some of these in the past for what it's worth. And it's used those agents to go and generate this comprehensive documentation that it's then gone and saved into some local markdown files for me. So that, I think, is pretty much all of the demonstrations that I wanted to get through today. If you're playing along at home, then there's basically a nice script that you can execute to clean up this environment. You can basically use the Azure Developer tool. And if I recall correctly, you can use a command called azd down, and that will go and delete everything that was set up when you were running the demonstration. But I'm not sure what time we're 1:10 here. So what I might do is I might just see if I can flick to the YouTube broadcast and just see if there are any outstanding questions on there that we can see about answering. So let me have a look. And let's have a look. So I can see straight away that Vanessa has been all over these questions, which is utterly brilliant. Internal storage to what happens when the Azure Functions restarted, dpatrick 957. Yeah, so that storage is persistent and durable. So it will basically hang around for as long as the durable task scheduler service is deployed for, which is great. I can see Vanessa's actually been awesome in here and has answered loads of these. So what I'll do then is I might sign off for today. So thank you everyone who stayed tuned in. Thanks for watching. I hope you've enjoyed today's session and have a great rest of your day. So thank you very much. Cheers. Oh, what I'll do actually before you go is I forgot I have got some QR codes. So we love feedback. Feedback is how we get better at these things. So let me pull the QR codes up. Take a look at these. And here we go. Feedback of your session. So please scan that. Leave us some feedback. And I hope you enjoyed yourself. Producer, I can't take myself off the screen, unfortunately, but let's call that a wrap for today. Thank you.